Today, I'm going to continue talking about random number generation. It's not that this is a particularly important problem. It's just that it's the greatest example to show you a lot of different techniques. So remember what our goal was? Our goal here is to generate a random number. So I want to generate a random number R, let's say. And this R is supposed to come from the set of numbers between 0 to n minus 1. So let's say I have a fixed number n, and I want to find a random number modulo n. Now, we saw that we want two really nice properties to hold. So these are our desired properties. And the desired properties were that I want this to be chosen uniformly at random. So the number R should be chosen uniformly at random. And the second property was that I want it to be tamper-proof. So no one in the system should be able to change R. So my first important property was uniform distribution. And the second property was that I wanted it to be tamper-proof. Okay. Now we've already seen two solutions. Our first solution was to just use a commitment scheme, a commit and reveal scheme, where everyone would just commit to the hash of their choice. And then after everyone has committed, everyone would be able to reveal, and then we would take the numbers given by all the participants and we would just sum them up modulo n. Or if n was a power of 2, we could also just XOR the numbers. Okay. So the guarantee that we had for uniform distribution was that even if one of my players is honest and is really giving me a random number that is generated from a uniform distribution, then the result will also have a uniform distribution. Okay. So this was a great thing, really. And the way we achieved it was, again, we just defined our R to be the XOR or the sum of all the RIs. And this RI was the submission of player I. And the guarantee was that even if one player gives me an RI that is distributed uniformly at random, then my R will also have the uniform distribution. So I need one honest player. Okay. Then we talked about tamper resistance, and we saw that that's actually much harder. So our problem was, especially in the commit and reveal scheme, what happens if someone does not reveal? And we saw that we can do all kinds of attack using that. So again, think of the case of lottery. If I have, let's say, half of all the tickets and I see that I don't win, I can decide not to reveal. And I cannot just say, okay, I'll take the sum of all the RIs that are revealed, because that allows an attacker to basically change the result. And if they're not winning, they will not reveal it. And if they are winning, they will reveal it. So, and also generally speaking, if you have, let's say, k tickets, you will have 2 to the power of k choices of what you want to reveal and not reveal. So you're kind of multiplying your chances of winning by 2 to the power of k. So that was our first problem. And then the other solution that came to our mind was, what happens if we say, whenever someone does not reveal, we will just redo the entire lottery. And we saw that that's not also good enough, because again, if you own half of all the tickets, and if you see that you're losing, you will just not reveal one of your tickets, and then the lottery will be done again, and you have a 50% chance of winning in the next round. And finally, the only solution that really worked there was to require a really huge deposit. So I had to make sure that every participant puts down a deposit that is worth more than the entire money that is at stake. And that wasn't very practical, but that was a solution. So we saw the first solution, which was deposits that are larger than the sum of the values of all the tickets. Okay. And again, this is ridiculous in the real world, because imagine that you're playing the lottery where there are 1 million players. So it means you have to put, let's say, $1 to buy each ticket, but you have to also put a deposit of $1 million every time, just to make sure that if you cheated, your deposit can be confiscated. So that didn't work that well. And this was the reason why in the previous session, we talked about secret sharing schemes. So what was the idea in a secret sharing scheme? The high level idea was that if you don't actually reveal your choice, other people will be able to come together and figure out what your choice was. So the idea of secret sharing was that you don't get to really choose whether you reveal or not. Even if you don't reveal, others will find your value of RI, your secret value. And when they find it, they will use it. So the R value here, the final random value, will be computed anyway, and you cannot change it. But of course, if you don't reveal, then you will be penalized. So there's also no incentive in the secret sharing scheme to do something dishonest. So in practice, everyone would actually reveal. So, but we saw that the secret sharing scheme also had its own problems. And again, if we want to look at these two properties, we had the first property that was fine. As long as we had one honest player, we would get a uniform distribution. But when it came to tamper resistance, we had to say that at least half of the players, are actually strictly more than half of the players, are honest. And this was like at the end of the previous session. So remember, the idea was that if I do a secret sharing with parameter T, it means that any T of the other players can come together and open the secrets, right? So it means that I should have at least T honest players who would open my secret RI if I don't reveal it myself. But then on the other hand, any T of the players could come together and open a secret at any time, including before the reveal phase. Right. So if I had T dishonest players that were somehow colluding with each other, they could actually violate the tamper resistance, and they could get any result that they wanted. So I have to have more than T honest players and less than T dishonest players. So this means that more than half of my players had to be honest. So basically, we have two solutions, and we don't like any of them. And today I'm going to give you a third solution that we don't like for a different reason. So our first solution, again, just to re-emphasize this point, was using a commitment scheme. And the problem here was that I needed large deposits. And I don't like to have large deposits. Our second solution was secret sharing. And the problem here was that we have to assume half of the players, or actually more than half of the players, are honest. And this is actually not very realistic if you think of it in the real world. So again, if you think about the case of a lottery, a rich person can easily buy more than half of the tickets. And if that allows them to win for sure, it's a great investment. So the assumption that more than half of the players are honest is not really a great assumption. This is actually very different from the Bitcoin assumption that said that more than half of the computational power should be honest. Because the idea in Bitcoin is that if you see that, let's say, a lot of the computational power is dishonest, you can just buy more hardware and start mining and contribute to the mining until a majority becomes honest. right? So in a sense, you have a way of fixing the problem in Bitcoin. But here, after the tickets are bought, if someone has bought more than half of the tickets, there's no way to really fix it. You cannot just keep selling more tickets. Okay, so these are the two problems we have. But actually, in the last session, when we were talking about secret sharing, we also had two really great ideas. So let's talk about that. Let's talk about some positive stuff here. We had two great ideas. And these were the two great ideas. The first idea was that if you don't reveal, it doesn't matter because other participants can actually compute your value. So that's a great thing. And we want to keep that. So if a player does not reveal, let's say, their RI, others can compute it. This was one of the great ideas. The other great idea we had was that if you wanted to cheat in the secret sharing, you had to cheat in phase one. You had to cheat in giving out the shares and everything. And at that point, it made no sense for you to cheat because you had to decide to cheat at a point where you didn't know anything about the result. So cheating was pointless. So this is the other point that we want to have. So we want to say that the players can affect the final result R. So for example, by choosing their RI or by choosing their hash or by choosing their shares, whatever, they can affect it only when they know nothing about other players' inputs. When they know nothing, actually, let's say it's like this, only when they know nothing about R. Right? So in a commit and reveal scheme, the problem we had was that the last player to reveal, if you were the last player and you saw that everyone else has revealed, you knew the current value of R, and then you could choose whether to reveal or not. But one of the great ideas in secret sharing was that you had to choose whether to give valid shares to other people when you didn't know anything about the value of R. So if you decided to cheat, that was a decision that you made before knowing R. And that didn't really affect anything because it's ridiculous to cheat like that. You're not increasing your chances of winning the lottery, but you're definitely going to lose your deposit. So in a sense, this is some disincentive for cheating, making sure that whenever you want to cheat, you can't really know if your cheating is going to help you. You cannot even compute an expected value and say that on expectation, my cheating will help me. So these are the two great ideas we had from secret sharing, and we want to keep this. So let's see if we can somehow apply these ideas to our original scheme where we had commit and reveal. Okay. So this is, again, a protocol that is not going to work, but I always do this. I start with something that doesn't work, and then we'll see how we can fix it. So this is my ideal protocol. My ideal protocol has several steps. So in my first phase, in phase one, every player chooses some inputs. So every player I chooses RI. And let's say that if they're an honest player, they're going to choose this uniformly at random. And then I want them to commit to this. So let's say that I have some commitment function. It's not necessarily a hash function anymore, but let's say I have a function that's used for commitments. So this player I computes some function, let's call it commit of RI, and let's call this commitment CI. So this player computes CI and records it on the blockchain, or records it in my smart contract. Okay, that's my first phase. And then, of course, during this phase, when the player wants to record the value of CI in the smart contract, they have to also pay a deposit. Okay, so I just here write plus paying some deposit. Okay, now in the second phase, I want my players to reveal. So phase 2 says that every player, again, let's call it player I, reveals RI to the smart contract. Okay, now what are the properties that I like to have in this ideal commit and reveal? Well, first of all, I want to make sure that my smart contract can really verify that the player had actually committed to this RI. Okay, so the smart contract, just write SC. SC verifies that CI is really a commitment to RI. Okay, so because I want to make sure that this player has not changed the value of RI. Okay, and otherwise, if that doesn't happen, if the given RI is wrong, then they will lose their deposits. Now, I want to have a final phase where I can say that if a particular player does not reveal their value RI, then the other players can compute the RI. Okay, so here I want to say for every player I who has not revealed, or who has revealed an invalid value, so who has not revealed RI, other players can find the RI, can compute RI, and they can also add it to the smart contract. So the smart contract always checks that everyone is doing the right thing. So I want these other players to be able to prove to the smart contract that this was actually the value RI that this dishonest player didn't give us. Okay. So these are what I like to have in an ideal protocol. And then, of course, at the end of it, I want to say that my random number is just the sum of all the RIs or the XOR of all the RIs. So now I want to talk about the properties that this commit function should have. What are the properties that this commit function should have? So in a traditional commit and reveal scheme, this commit function is just a hash function. So let's just start with writing down the properties of the hash function, and let's see which one of them actually create problems for us. So what are the properties of commit? So what were the properties of a hash function? This was lecture 1, 19 lectures ago. And I don't care about the puzzle friendliness part for now. So basically, a hash function was collision free and it was hard to invert. Right? So those are the two things that I care about at this point. So it was, first of all, so collision free. And this means that it is impossible. And by impossible, again, I mean impossible in the lifetime of the universe or something like that, not mathematically impossible. So it is impossible to find two values, x and y, that are not the same, such that, well, the hash of x is equal to the hash of y, but here I'm not talking really about a hash function, I'm talking about a commitment function. So I just want to write some desired properties for this commitment function. So I want to say it is impossible to find two values such that commit of x is equal to commit of y. Okay. Can I relax this? Can I say that I don't want my commitment function to have the collision-free property of hash functions? Not really, because that's the whole point of a commitment, right? So if there are two different values of x, if as a player I can somehow find two different values, let's say x and y, and my commitment to x would be the same as my commitment to y, then I can just publish that commitment. And then when it comes time to reveal, I can choose. I can choose if I want to reveal x or I want to reveal y. And that will, of course, give me an undue advantage. And this is against the tamper-proof property. So I want to make sure that I keep the collision-free property of hash functions. But hash functions had another property that is actually problematic for us. So yeah, let's say keep this one. But the other property was that they were basically hard to invert. Okay. So another way of thinking about this is that given a commitment CI, which was the result of committing to RI, it is impossible to compute RI itself. Okay, or we also call this the hiding property for hash functions. So basically, this was a property that we had in the hash functions, and in this particular use case, it meant that if I commit to a random value and put that commitment CI into the smart contract, then no one else can actually compute my random value, RI. But this is kind of the opposite of what I want. Right? So I want to say that even if I don't reveal, others should be able to somehow compute it. But they shouldn't be able to compute it instantly. It should actually take them a lot of time. So what do I really need here? If I'm a player, I'm going to give my commitment CI in phase 1. And I have to make sure that no one else can find the value of RI, my random number, in phase 1. Because if they find out the value of my random number, then they can tamper with the result. Right? But actually, when time passes, when I get to phase 3, I want others to be able to compute it now. Right? Because when it gets to phase 3, I want to say that if I were not honest and I did not reveal in phase 2, then others should have been able to compute it. So I don't want inverting this function to be so hard. I don't want it to be impossible. I just want it to take a lot of time. I want it to be so slow that I can be sure no one can do it while we're in phase 1, but everyone can do it by the time we reach phase 3. Okay? So that's ideally what I need here. So I'm going to say change this one. And maybe instead of hard to invert or impossible to invert, let's make it time consuming to invert. So here I'm going to say, instead of given a commitment CI, it is impossible. And again, remember, impossible meant that we can't do it in the lifetime of the universe. Instead of saying that it's impossible, I'm going to say it takes a lot of time. I'm going to say it takes at least some time, t units of time. Okay. If I had a commitment function like this, then I could also set the timing here so that maybe phase 1 and phase 2 together, they take, like, let's say, t units of time. Or maybe even less. Maybe I want to be safe and I say I allocate only half of t to these two phases. And then phase 3 is everything that comes after. Okay. So again, if I had an ideal commit function like this, and by the way I'm speaking, you know that I don't have it. But if I had something like this, then my commit and reveal would actually work pretty well for generating the random numbers, right? Because again, let's just go over this one more time. Each one of the players is committing to their value Ri by publishing Ci in the first phase, right? So at this point, only player I knows what Ri is going to be. From the point of view of every other player, it's not possible to know it because they just know Ci, and in order to compute Ri from Ci, they're going to have to spend t units of time, and well, they don't have that much time, right? And then in the second phase, when the players actually reveal their values, the smart contract can easily verify it. But actually, I have to maybe add this as a property here as well. One other property of hash functions that I want to keep is that they were easy to compute. And by easy, I mean that it takes very little time, right? And I want to keep this property. So if I have this Ri, it's super easy to compute the Ci. And then here, when I reveal it, again, for the smart contract, it's super easy to verify it. And I want this to be easy because I'm paying gas for this part, right? And then after phase 2 ends, we have a bunch of cheaters. We have a bunch of people who have not revealed their value of Ri. But then now we have all the time in the world. And we can wait for the other people to actually compute the value of Ri that the cheaters did not disclose. And when someone else discloses the value of Ri, again, the smart contract can verify that this is the right value. So the verification is always super fast, but the computation is time consuming. Okay. So this is the kind of function that I like. And unfortunately, I don't have, and I will tell you why I don't have this kind of function. But I have to first talk about this part. What does it mean when I say it takes at least t units of time to compute this function? You see, when we were talking about inverting hash functions, we saw that inverting hash functions is basically proof of work. That's like how Bitcoin is made entirely. So it's super hard. You have to just try a lot of random numbers before you can find something that inverts your hash. But here, the problem, especially in proof of work, was that you could parallelize it, right? So for example, when you're doing Bitcoin mining, your chances of adding the next block, your chances of successfully inverting the function is actually proportional to your computational power, to the number of hashes that you can compute in every second. But I don't want that here. So I don't know anything about the computational power of my players. Right? These are just some people who are taking part in this lottery. So some of them might have vastly more computational resources than the others. So I want to make sure that it takes t units of time for all of them. I want to make sure that you cannot parallelize the computation that you need to do here. So in other words, I want to say that it takes at least t units of time, no matter how many cores or threads you have. And actually, the word that people use here, and we're not going to cover that too much in this course, but you can Google it, is called proof of sequential work. So I want to have a function that is hard to invert, and also parallelizing shouldn't help me. I shouldn't be able to get any, well, I cannot say I don't get any benefit, but I have to get very negligible benefits from parallelizing. I shouldn't be able to make it like twice as fast. Okay. Of course, here, all I need is that if I have a timing like this, if I give t/2 time for the first two phases, I just want to make sure that no matter how much computational power you have, you cannot reduce the runtime from t to t/2, right? And of course, instead of 2, I could use any other constant. I could use t/100. So I just want to make sure that no matter how much computational power you have as a malicious player, you cannot find the values of the other players while they're still in phase 1. Okay. Now, why can't I have a function like this? What's wrong with this function? Why is it impossible? So the problem here is that suppose I had a function like this. Well, actually, maybe I can have a function like this, but my point is that even if I have a function like this, it will not help the way that I hope it would help me. So let's say I have a function like this. Is this function one-to-one, mathematically speaking? It cannot be one-to-one for the same reason that we said no hash function can be one-to-one, because you're mapping strings of any length to a fixed length, right? So this is not one-to-one, which means that there are two values, x and y, that have the same commitment. It's just that we assumed it's impossible to find them. But this one actually contradicts this one, because I can just take a random value x and I can compute commit of x. And then I assume that I can invert it in time t, right? So I just apply whatever inversion function I have in time t, and I find another value y that has the same commit. Okay, so actually, another way of looking at this is that if I'm a malicious player here, I start my maliciousness before even phase 1 begins. I find two values that have the same commit, and I can find them if I have this property. It just takes me t units of time. And after I do that, I commit to one of them. I mean, well, I publish the shared commitment value. And then in phase 2, when everyone else is revealing, I again get two choices. I can reveal either x or y. So we're back to square one. We're back to where we were with basic commitment schemes. Okay. Or another problem here, actually, which is very similar, is that if this function is not one-to-one in the mathematical sense, then what happens in phase 3? So let's say I had a malicious player I, that player was dishonest, they did not reveal anything in phase 2. Now in phase 3, there is not a unique RI. You have many different values of RI. And it might be that different honest players find different values of RI. So you don't have a well-defined output here. Well, your output R depends on the RIs. So basically, we need the function to be one-to-one. And if we do that, again, we don't really have a function that has all these properties and is also one-to-one. At least we don't know how to make it. So sorry, this was just a thought experiment to show you what would be good. Like if we were in an ideal world, I would like to have something like this, but we don't have it. But we have something that is close enough. And this is what I'm going to introduce now. This is called a VDF. And a VDF, it stands for Verifiable Delay Function. So what is a verifiable delay function? It's basically a function that is hard to compute. We're sure that it takes at least t units of time to compute. And we're also sure that parallelization doesn't help. So no matter how much computational power you have, it's going to take you t units of time to compute. So a verifiable delay function is going to have two parts. So this is like the formal definition. It has an evaluation function, basically. And the way it works is that you have a function called evaluation. You give it some string x, and it outputs two things. It outputs a string y and another string p. So the idea here is that if, let's say, I'll call my function f, then f of x is supposed to be y, and p is a proof. P is a proof that shows that y is really f of x. Okay, so let's say that I have a function f, and this maps my strings to strings. And let's say that I have a fixed length for my strings. And this is, let's say, 1-to-1. Okay, so when I do the evaluation, I get two things. I get y and p. And what this means is that f of x is y, and p is a proof. P is a proof that shows f of x is y. If you passed complexity theory or something like that, this should remind you kind of the definition of NP. Okay, and then we also have verification. So we have a verify function, and this verify function basically gets x, y, and p, and gives you either true or false. And so it returns true if y is f of x and p is a valid proof that y is f of x. But it gives you false if y is not f of x, or if y is f of x but p is an invalid proof. So basically, the way you have to look at this is that I have a function f, and I have two operations. One operation is that I give my function f some input x. I get the output of my function f, which is y. And I also get a proof that this y is actually the output corresponding to x. The other action that I can take is that I can do verification. So if someone gives me an x and a y and claims that y is f of x, and if they also give me a proof p, I can then verify if that's a correct proof. I can verify if it's true or false. Okay, and of course, the important points here are the timing. I want this one to be fast. So I have to be able to verify it super fast, but I want the evaluation to take at least t time, t units of time. And again, this is assuming that you have all the computational power in the world and you're doing all the parallelization in the world and you're using the best possible algorithm. It doesn't matter. You cannot do the evaluation faster than t. It turns out we have functions like this. Okay, so again, just like the case of hash functions, I'm not going to tell you how to create this because it gets into a lot of details of hardware and things like that. I don't want to do that. I want to teach you cryptocurrencies. So what are the properties that I need to have? Well, of course, I need to have the uniqueness property. And my uniqueness property basically, well, I don't necessarily need this to be 1-to-1 right now. Let's say I have a function f. My uniqueness property is that for every x, there should be one y. So I want f to really be a function. I don't necessarily want it to be one-to-one. So I want to say for every x, there exists, and when I write it like this, I mean there exists exactly one y for which there exists a proof p such that the verification passes. Verify of x, y, and p is true. Now, here's the thing. If y is f of x, I want this verification to pass for some proof. I mean, even if y is f of x, I might have a wrong proof and then it might not pass, right? But if I have the right value of f of x, which is y, and if I have a right proof, then I want it to pass and give him true. And very importantly, for every x, I want to have a unique y, but I don't necessarily want to have a unique proof. So you can have many different proofs for the same y. That's fine, that's allowed. So this is my first property. And my second property is what we call epsilon sequentiality. And I'm writing this so that you can Google it if you like, because I don't want to give you a formal definition. All I want to say is that you cannot find any information about y if you have x and you spend less than t time. So given x and spending, I can't spell, and spending, let's say, t times 1 minus epsilon time, you cannot find anything about y. Okay. So let's say I have a function like this. Basically, I have a function that's hard to compute. If you want to compute it, it takes you at least t time. But if you compute it, you also get a proof of your computation. And then if you give the result and the proof to someone else, that someone else can easily verify that you computed the function correctly. These are the properties that we have in a VDF. Okay, how does this help with our system here? So can I just put a VDF in place of comments? Unfortunately, no. Okay, what happens if I just put a VDF in place of comments? So first of all, it takes a long time for anyone to want to commit. So if you just start, if you're a player and you join here in phase 1, you don't have enough time to commit because just committing takes t units of time now, right? So that's the problem I have here, because that's the reason I cannot just put a VDF into this process like this. But actually, assuming that you somehow magically could compute this in time, then the rest of the protocol would work, right? So if this commit was a VDF, and if you didn't open it here, then in this phase, someone else could open it and could give the proof and everything to the contract, and then the contract could do the verify, right? And calling the verify function, that's something that is cheap and takes very little time. So what do we do? Well, basically, we cannot have a call to our VDF here, because the role of a VDF is generally to slow things down. So whenever you want to compute a value of a VDF, it's going to take a lot of time. It's going to take t units of time. So you cannot evaluate a VDF in phase 1 of your protocol here, because you will run out of time. So let's just not do that. Let's change our protocol so that the only phase where we evaluate a VDF is after phase 1. So this is my protocol now. So let's call this VDF-based RNG. So verifiable delay function and random number generation. Okay. So here's what I'm going to do. I'm going to say in phase 1, every player I just submits RI. So we're not going to commit to RI. We're not going to hide RI. We're just going to give up RI. So submits RI to the smart contracts. Okay. So there is no revealing or anything like that. Now, this is phase 2. In phase 2, I'm going to actually use a hash function. I'm going to say that H is the hash of all the RIs. So hash of R1, R2 to RI. I can also just use the sum. I can also do something like this. I can say H is the sum of all the RIs. From 1 to whatever the number of players were. So I don't know, let's say we had P players. Okay. I don't care what this H is. It can be the hash of all of them. It can be the sum of all of them, modulo n, or whatever. What I really care is that I want to have a value H that depends on every single one of those RIs. And then here's my last phase. I say my random number R, which is the final result of the entire procedure, is going to be a VDF of H. So we don't have commits or reveal. We just basically give out our value of RI. There is no revealing or anything. Why does this work? And let's say that this VDF is with parameter T. So it takes T units of time to compute. And let's say that for these two phases combined, I gave T over 10 units of time. Okay. This works because of our second great idea that we had here. Our second great idea was that players can affect R only when they know nothing about R. Okay, so how can my players affect the value of R? They can affect it by their choice of RI, but they're choosing their RI in phase 1. And in phase 1, they don't know anything about R because they cannot run this VDF because this VDF takes T units of time and they don't have enough time here to run that. And based on this assumption, we assume that if they have even like a factor of epsilon less than T time, they cannot find any information about it. So even though they're seeing the RIs of all the other people, they have no idea what the output of this VDF is going to look like. And because they have no idea about this output, there's no way for them to cheat. They can give you any random number RI. And I mean, it doesn't even mean anything to say they're cheating because like they don't know anything. What are they really affecting here? And then, of course, after phase 1 and phase 2 ends, everyone can compute R because H is just computed, let's say, in the smart contract, and then it's just an evaluation of the VDF. So anyone can compute the evaluation of the VDF. And of course, very importantly, we don't evaluate the VDF on chain in a smart contract because then we will have to pay T units of gas, which will make us bankrupt. But someone else, one of the players outside, computes this VDF, spends the T units of time, and then in phase 4, they submit the value of the VDF to the smart contract. So someone, it doesn't matter who, submits R and a proof P. And this is a proof that R is really the correct VDF to the smart contract. And the smart contract verifies it. So again, this P, it was a proof of this equality. And then the smart contract does this. It does verify of H, R, and P. So it verifies that R is the right VDF output for the value H, which was also saved in the smart contract. Okay. Now, as you see here, we actually used both of our great ideas from secret sharing. So the first idea was that if a player does not reveal RI, others can compute it. In this case, we just said, to hell with it. We don't want to have revealing or anything. We're just going to let everyone be able to compute the VDF. And that's what's happening in the last phase, right? And the second great idea was that players can affect the final value R only when they know nothing about R. And again, here they can only affect R by their choose of RI, but they don't know how they are affecting R. And they don't know how R looks like right now before they're submitting their RI, because any computation of this VDF is going to take T units of time, and we just don't have that much time. Okay, so it seems we solved the random number generation problem, and we're out of time for this session as well. But actually, not really, unfortunately. So we found a solution that gives us perfect tamper resistance. But actually, somewhere along the way, we lost this one. We don't have uniform distribution anymore. Because remember, when my output was just the sum of all the submissions by all the players, I could say that even if one player is giving me a truly uniformly distributed number R, number Ri, then R will also be uniformly distributed. But here, my R is coming as the output of a VDF, and a VDF looks very much like a hash function. So it's not predictable, but there's also no guarantee that it's uniform randomness. It's just tamper-proof randomness.